Good day, everyone. Today, I'll be discussing Euclid's contributions to number theory, particularly his work on prime numbers and divisibility. While Euclid is widely known for his contributions to geometry, his work also laid the foundation for modern arithmetic and algebra. So now, let's explore some of his key ideas with examples to make it clear and simple. First, Euclid elements, especially in Book 7, 8, and 9, focus on natural numbers, the counting numbers like 1, 2, 3, and so on. Euclid built upon earlier work such as that the Pythagoreans, but he gave it more logical and structure. For example, instead of symbols, Euclid described using line segments. This was his way of explaining arithmetic, which we now do with algebra and modern symbols. Number 2 is prime numbers. Prime numbers are the numbers divisible only by 1 and themselves. Here are some simple examples. 2 is prime numbers because its divisors are only 1 and 2. 3 is prime numbers because its divisors are only 1 and 3. 4 is not prime numbers because it's divisible by 1, 2, and 4. It's interesting to note that 2 is the only even prime number because, as I said, the only divisors of 2 is 1 and 2, which is prime number also. Next is Euclid's proof of infinite primes. Euclid proved that there are infinitely many prime numbers. How? Let's imagine you list some prime numbers like 2. We will write 2, 3, 5, and 7. And if you multiply them together, like 2 times 3 times 5 times 7 equals 210. Since 2 times 3 is 6, 6 times 5 equals 30, and 30 times 7 equals 210. Then, we will add 1 to 210 so that we can get the new prime number. So, 210 plus 1 is equals to 211. The new number 211 is not divisible by any of the primes on our list. So our list is 2, 3, 5, and 7. So 211 is not divisible to any of our primes that are in list. This means either 211 is a prime or it is divisible by a new prime. So, no matter how long your list gets, there will always be more primes. And now, let's proceed to fundamental theorem of arithmetic. This theorem states that every number greater than 1 can be written as a product of prime numbers in only one way. For example, 30 is equals to 2 times 3 times 5 since 2 times 3 equals 6 and 6 times 5 is equals to 30. Another example is 60 since 60 is equals to 2 times 2 times 3 times 5. Since 2 times 2 equals 4 and 4 times 3 equals 12 and 12 times 5 is equals to 60. No matter how you factorize, the prime numbers will always be the same. And now, let's proceed to divisibility and greatest common divisor, or the GCD. Divisibility means one number divides another without leaving a remainder. For example, 4 divides 12 because 12 divided by 4 is equals to 3, so there is no remainder. 5 does not divide 12 because 12 divided by 5 is equals to 2, with a remainder of 2. So 5 does not divide 12 because there is remainder. And now, let's move on to the greatest common divisor, or the GCD. The GCD is the largest number that divides two numbers evenly. For example, find the GCD of 12 and 30. So now, we will make a list of the divisor for both number 12 and 30. And now I have here the list of the divisors for 12 and 30. So here are the divisors for 12 and 30. So the divisors of 12 is 1, 2, 3, 4, 6, and 12. And the divisors for 30 is 1, 2, 3, 5, 6, 10, 15, and 30. So the common divisors of 12 and 30 is 1, 2, 3, and 6. Since we will find the greatest common divisors of 12 and 30, so we have here the 6, which is the greatest common divisors of 12 and 30. For the last, we will proceed to Euclid's methods. Euclid didn't have modern algebra. Instead, he used geometry to represent numbers. He described numbers as line segments. For example, saying 6 measured 12 is the same as 6 divided by 12. In summary, Euclid's work on number theory has shaped mathematics for over 2,000 years. He proved prime numbers are infinite. Every number can be uniquely factorized into primes. Concepts like divisibility and GCD, or the greatest common divisors, are foundational to arithmetic. His logical approach continues to inspire mathematicians today. That's all, and thank you.